So just get started. Start off with a quick introduction as to what are online payment systems, who am I, why do I talk about this, what can you do with the types of attacks that I'm presenting, and how do you go about doing them. Not necessarily in that order. I just want to make clear that this is not a PCI talk. If you somehow thought that I was talking about PCI compliance, it's the wrong one. I'll try to avoid naming individual payment gateways because these issues affect pretty much all of them to some degree. And if I were to sort of showcase payment gateway X and you think that I move to another one, I'll be safe. You probably aren't. So I don't want to sort of point any fingers. Sorry. And one of the other things is that most of the plugins for open source tools like OS Cumulus, Sendcard, whatever, they're often written by a third-party developer and not necessarily vetted to the payment gateway vendor standard. So as far as like implementation bugs go, they vary a lot. Sorry, I'll try to avoid some feedback. Right, there's a bit of my credentials. Married, got 2 kids, work as a penetration tester, bit of a tech head geek. I write a blog, kind of pretend to write a blog. I don't think I've updated it in like a year and a half. I run a few projects, mostly aimed at identifying security flaws or exploiting vulnerabilities. So primarily aimed at, I guess, penetration testers and bug hunters. I also contribute to some well-known open source projects in what little spare time I have. So, jumping into it, payment gateways are effectively the point of sale system for a web shop. So in a normal shop, you walk in, you walk up to a cash register, you hand over cash. The payment gateway is the equivalent in the web sense that you run a website, you want to do some sales. The payment gateway is effectively the cash register, but it's typically outsourced to somebody else. So, quick introduction. We'll talk a bit about what are the actors in a normal online transaction. Talk about some definitions. We'll look at payment gateway APIs, and then we'll move on into the actual design vulnerabilities. Talk a bit about the use of cryptography, and finally, we're going to discuss some implementation bugs. I got a couple of demos for most of these things. So we'll start off with the customer. Just, happy guy wants to shop online, get his stuff delivered to his door, and not have his credit card details stolen. The merchant, he wants to supply the goods or services, wants to make it cash, and most of the design flaws in this presentation actually affect the merchant, not the customer or the bank or payment gateway at the end. So the payment gateway, typically large financial institutions or in some cases small startups, they take a fraction of each transaction typically and basically that's how they generate their money. And then there's the attacker who, I suppose, scans the internet for things to destroy, if you believe popular press. In this case, it would typically be either bored kids or organized crime. While the attacks that we're going to discuss don't really scale to sort of millions of dollars of damage unless you do them across the internet, there's still enough traction, I think, that organized crime would be willing to repeat these type of attacks over and over. However, we don't really see them in the wild, just because it's easier to steal, 80 million credit card numbers from some random corporation. But I suppose as things get more and more difficult, we might eventually end up seeing some of these attacks. I've been working with several payment gateways for the last 2 years. There are mitigations in place for a lot of these attacks, but there isn't really any sort of incentives for the customers to move on. And so I think while there's sort of a lull between these things aren't being exploited in the wild and a solution exists, it's sort of time to try to push people to move on to a safer alternative. Sorry. So If you're a pen tester or sort of implementing a payment gateway, or we want to play around with them, you should use test card numbers so you don't have to charge your card all the time. So these are typical numbers that I tend to put into any sort of payment form when I'm doing penetration testing. There are often additional numbers that might be specific to the payment gateway that returns certain behavior if you wanted to test for insufficient funds on a card or card cancelled, etc. You can usually find that sort of information in the developer's guide from the payment gateway. So it's always worth having a look at the developer's guide or the documentation when you're testing these type of things, because there might be bugs in the implementation, in the integration, etc. So, all right. The primary means of utilizing a payment gateway when you run a website that you want to sell stuff is through an API. And the typical operations from an API are things like charging a card, querying the status of a card, pre-auth in some case if you're like a hotel or a camping place where you want to take a deposit but not necessarily charge them. Manage your recurring payments if you offer subscription services, and refunds for unhappy customers. They're typically accessed through two environments. There's the sandbox, which is what you're meant to be using when you're developing your plugins or integrating with the payment gateway. That's an environment where it's fine to fail. It won't actually charge your cards. It's a playground. And then there's production. Now the details, the merchant account configuration is typically shared between these two environments. So if you are an attacker, it's better to test your exploit against the sandbox, because if there's something wrong with it, like you have a typo or something, the sandbox will basically give you a nice error message saying that you made a mistake. But it won't throw up any flags in sort of fraud detection systems typically, because they don't monitor the development. So an example of that is trying to bypass or playing with an actual redirect type payment. The sandbox goes, you got invalid account configuration, please contact the merchant. And so you can tweak your exploit against the sandbox until that works, and then move on to production from there. So looking at how the various transactions work for the different ways to implement the payment gateways. The direct API is something that we see a fair bit. Typically this means that the merchant carries the burden of being PCI compliant, because they receive the credit card data directly to themselves and then pass it on to the payment gateway to charge the card. So we'll start with being on the checkout page. You'll do a post directly to the merchant website saying, here's my credit card numbers, the amount that I want to pay for the goods that I'm buying. Then when the merchant data receives it, they go ahead, they make a SOAP request to the payment gateway. In this case, authentication is enabled, and so you wouldn't be able to impersonate, say, the merchant, because you would have to know the username and password. Then payment gateway charges the card, sends back a status, whether or not payment was received, there's a receipt, more information than that. And then based on that, the merchant will send back some HTML saying payment was successful, or payment failed, please try again, contact support, whatever. So that's sort of the very straight and narrow, simple implementation, but it has the PCI requirements. So a lot of people are moving on to things like a hosted payment solution where the payment gateway takes the credit card details directly. So the merchant doesn't actually have any involvement in the payment transaction. And that way you avoid having to be PCI compliant. But it means that there's a disconnect between the merchant and the payment gateway. And so there's some room there for abuse. And so we'll start with an example of this. You get the checkout page, it sends back HTML, and there's a straight post from the browser to the payment gateway, which effectively means that the customer is making the API call on behalf of the merchant. It basically means that the API for the payment gateway for this merchant is kind of public. And so if you were able to work out certain details that are used to validate that this is a legitimate merchant account, you could mess around with these figures. So post goes directly to the payment gateway with your credit card details. Payment gateway sends back a redirect saying, yeah, I've charged you. Now please go back to the merchant gateway and provide the following details. So as you can see, there's a whole bunch of data here in the in the redirect saying, here's the payment amount, etc. Then the browser says, yep, redirects to the merchant website. Merchant website receives the details, and then based on what the browser provides, determines whether or not payment has been received, gives you a receipt. Might initiate pick in place if you're one of those. Say if you're running OS Commerce or one of these popular solutions, they often have integration for pick in place or warehouse shipping. So they might not even validate that the funds clear and goes into an account. It'll get shipped straight away. Different alternative is without using a direct post, you take it to a white label page on the payment gateway before doing the post with the credit card details. So same kind of stuff. You go to the checkout page. Checkout page, in this case, redirects you instead of giving you a HTML form. And as you can see in here, there's all the payment data in the redirect. You send that to the payment gateway. Payment gateway sends back a HTML form saying, all right, please give me your credit card details. You send the credit card details, and then the payment gateway charges the card, sends you back to the merchant website saying, okay, well, here's the details to provide the merchant, transaction ID, etc., which your browser sends to the merchant, and the merchant then decides whether or not, to issue a receipt, ship, etc. So same kind of deal. There's also an alternative which some people believe offers more security, which is essentially the same thing, but so you go to the checkout page, redirect back to the merchant gateway, and the merchant gateway sends you a form. You post credit card details directly to the payment gateway, but instead of the payment gateway redirecting you back to the merchant with the details, it makes a post request directly to a hidden URL that supposedly only the merchant and the payment gateway know. So that'll make the post request there. Merchant then knows, okay, well, payment has been received. And then the payment gateway just basically redirects you back to like a thank you page. So you're not giving transactional details or receipt details through the browser this way. And it's potentially harder for an attacker to know where the endpoint is to attack the, yes, I've paid you, here's the details URL. So there is a logical fallacy with that, and that is if you're using an open source solution and you're using a plugin, so say your OS Commerce, and you're using plugin for this type of payment gateway, the return URL is always the same in the plugin. So, it might be hidden, but at the same time, it's known. If you go look at the source code, you'll find it. If it's a custom implementation, humans still tend to name things in a sensible manner. So you can usually just go looking for things like return or payment received type of pages on the website, and you'll typically find it. So to finish this up, it goes to the straight HTML page and just says payment received. There's also a third integration, which is where the merchant directly speaks to the payment gateway, so there's no customer involvement. A typical example of that is when you refund money. The customer's called up and said, you sent me an iPad and the screen was broken, I'll send it back and give me my money back. So the customer has no involvement in this, even though there's been a prior transaction. It's just basically a straight up SOAP request, typically. And you're done. Money gets refunded to the customer. So if an attacker were to go after any of these type of transactions, there's typically two ways you do this. You either go in on this component where it's transmitting the transactional data to the payment gateway. So the URL might do a 302 redirect, and URL will have things like the amount, $1,000. You go change that to $1, and then you complete the payment, and hopefully the website on the other end doesn't validate that the payment amount matches. It just goes, yep, status is paid, here's the receipt number, and it ships you a new iPad or a laptop, whatever. And the other thing that's typically done is to just bypass the first steps. So you go straight from the checkout page, and then you go to the thank you, payment has been received page, and you just spoof a transactional detail. And since the merchant is disconnected from the payment gateway, they might not have a way to validate whether or not these details are correct. And so there are several CVEs assigned to these type of attacks. I think the oldest one I found goes back to 2002. But those are only the vulnerabilities that have been given a CVE. I mean, these things date back to early 80s, probably. And it's still largely a problem. So, traditional attacks, change the payment amount. Just in the URL, change it to a cent. And they solve this with something that they call request validation. Or you spoof the payment received, and they solve this with response validation. Now, you might ask, what are request and response validation? It's basically a fancy name for a message authentication code. Typically, it's also referred to as fingerprint, signature, etc. But they hash the details, and then they send a hash along with it. And if you change the amount in the transaction detail, the hash no longer matches, and the transaction gets aborted. So examples of request validation, typically it only protects the vital components of the transaction. So the actual URL in a redirect is quite big, and will often contain things like the customer information, transactional data, description of items bought, etc. And so they don't hash the whole thing, they just tag these are the things that we think are kind of important to validate whether or not the transaction is valid, and make sure that they don't change the amount or the currency. So some examples of this, straight up SHA-1. So these things, the blue details are the account ID, so the merchant account reference. The red is a shared secret, which is meant to ensure that people can't just generate different hashes, because they won't have all the messages, or instead of an initialization vector. MD5, different order of things, and the other one has an MD5 or an MD5 plus the secret key. And as you can see, each implementation is slightly different, but they're also very similar. And so when you're dealing with payment gateways, each payment gateway has their own way of doing things. So from a sort of implementation perspective, they're slightly different, but from a design perspective, it's the same thing. It's like, yep, you're generating a hash, and the hash consists of values plus your secret secret. Response validation is the same thing, only protects the vital details. Typically, that's just the merchant ID, the transaction ID, and the amount. So examples of that, you can see they're almost the same as the initial amount, or the initial example, which was request validation. So request validation is applied by the merchant when it's sending the customer to the payment gateway, and then the response validation is used by the payment gateway when you're sending the user back to the merchant. And so the shared secret is known to both the merchant and the payment gateway, so otherwise they couldn't possibly validate it. So when you're dealing with request or response validation, you have a couple of options. You can bypass the validation, you can abuse some of the cryptographic properties, or you can defeat validation, which eliminates the use of signatures altogether, really. So typical ways to bypass it is HTTP parameter pollution. So basically, you define the same parameter more than once. Hopefully, if it's vulnerable, the hash check, signature check will use the first parameter, and then the actual charging code will use the second parameter. A typical example of that is, a PHP page receives it and then sends it to a SOAP backend, where having two elements defined in XML will cause XML to use the latter. You can abuse unprotected parameters. So since they only protect the vital parameters of the transaction, say if you're buying a subscription service, you can just modify the expiry date. So you're still paying the full price, but instead of having the service expire after a month, it'll expire after a century or more, which basically means that you're getting a lot of stuff for free. There's also abuse of application logic. So examples of this is enabling pre-authentication or pre-auth for payment received. And some payment gateways have this where instead of having transaction details change in order to make the transaction change from a charge to just pre-auth of an amount, they have an additional parameter which isn't part of the signature. So you append this parameter, and instead of charging your card, it generates exactly the same details back to the merchant, but with the additional parameter of pre-auth 1. And so if the validation code doesn't check for the presence of pre-auth, all the other parameters are identical, and so it'll go, well, I've been paid $50, but instead it's just pre-authorized $50. So if you can't use any of those, you might be able to attack the crypto. So in the examples that we saw, they're using MD5, SHA-1. Now, they're typically vulnerable to length extension attacks. It's a lot easier on MD5 than it is on SHA-1. But I'm sure we'll see research to eventually defeat SHA-1 as well. If you don't know what a key length extension attack is, the short description is that the hashing algorithm works on a chunk, a set amount of bytes. And then if it doesn't have enough bytes, it'll pad. And if it has more bytes, it'll sort of compress the middle section a bit. And what you can do is, without knowing the key, which is K in this case, you can add padding and then append a different message, which is M2 in this case. And because of the way that the blockchaining works, you will actually discard the unknown data and sort of override it with your data. So you can have two different messages, or you can append padding and a different message to the non-details of the signature, transaction data, and actually have the hash collide. And then that way you could pass validation checks. Sadly, length extension attacks are pretty costly. I wouldn't, you have to do it on a per transactional basis. Finding MD5 collisions even is, with all the advancements in crypto, it's still a CPU intensive exercise. So there are a much better solution. We can just defeat the request validation. And the way you go about that is you look at how the fingerprint is made. So these are the details that the server-side script on the merchant website used to generate the request validation. So, vital details, there's the merchant account ID, there's the secret shared key, transaction type, reference ID, an amount, and a timestamp. And then the browser submits the following information to the payment gateway. There's a merchant ID, transaction type, reference ID, amount, timestamp, and a fingerprint, as well as a result URL. There are often additional parameters, but these are the ones that sort of matter. So if we compare them side by side, you see that they are basically the same. Now, some of you might already see the problem here, but let me highlight that for you. We have an unknown password and an unknown hash with a whole bunch of other plain text. So effectively, we can treat the rest of the plain text as salt and just apply standard password cracking techniques. Now, the shared secret, it's usually vendor supplied, it never changes, in fact, there is no option of like changing it. You have to open support request, wait for like a week, and as soon as they change the key, your website is broken because you have the wrong key and now signatures don't match anymore. So typically it never changes. Furthermore, it's often converted to uppercase or lowercase just to make it easier for developers not to screw up. But that just stacks the odds further in the attacker's favor, because now your key space that you have to brute force is significantly reduced. So an attacker could just sign up to the payment gateway that they're looking to abuse, receive one of these codes, and because they supplied by the vendor, that will typically let you know how long it is and what kind of complexity you're dealing with, and then you just optimize your password cracking code for that. So what I've usually seen in the wild, I suppose, when I've done pen testing, is typically it's 8 characters of bad to really bad, I suppose, complexity. There are some that includes meta characters, but they tend to be safe, and so to prevent things like an apostrophe breaking it because of SQL injection, they tend to stick to sort of uppercase, lowercase. And even if they use uppercase, lowercase complexity, sometimes they cast it to uppercase or to lowercase and they actually defeat their own password complexity. In general, I know one other payment gateway that uses 10-character passwords. There might be more than this particular one, but even 10 is not strong enough. The big card vendors use 32-character hex value, typically derived from a HSM. And the ones I have spoken to are already in the process of moving to a 64-character shared secret. And if you're dealing with those, you have to fall back on the key length extension because you can't crack them in a human lifetime. So, when you want to crack this, you can move to the cloud because everything's in the cloud these days. Why use the cloud? Well, rather than going out and buying dedicated cracking hardware, setting it up, you can just hop on Amazon, launch a couple of instances. Amazon offers GPU. Don't think Google does it yet, but I'm sure it's in the pipeline. Find a readily available image, so you don't even have to do the install. And typically there's like a shell script that you can just run that will install all the development libraries for you. And within 5 minutes of hitting start on your instance in Amazon, you're up and running. And you can also make that elastic if you're not using GPU because you can't elastic graphics cards. So you can, for example, use John the Ripper. John the Ripper has great support for dynamic formats. I recommend getting the Jumbo distribution. It comes with all the good user-supplied patches. It supports distributed cracking over MPI, so you can fire up as many instances as you want, or you could just use Elastic because John the Ripper doesn't require GPU. You can also use both CUDA and OpenCL with John if you're using the Jumbo distribution. However, the CUDA libraries or the CUDA code is sadly lacking, and the OpenCL is not really optimized for performance. So while it is available, if you're happy to write your own OpenCL or CUDA kernels, I don't see why you should not use John the Ripper for this. So what you can do is you can go in and just define dynamic format. So in this case, oops, can't put a line. So just created signature there, and then down here, we'd say, take a clean buffer, start by adding some salt, then append the password, add some more salt, and then encrypted MD5. And effectively, we include a test which contains this bit here is the end result hash. Here's the first salt, here's the second salt, all the way down there. And that's what the password would be. And then you can validate that with using John --test format, the format that you've defined. If you are using John, I would recommend that you also update john.conf, use a specific john.conf to make sure that you match the password complexity in characters as well as which character sets you're using. So otherwise John will waste a lot of time cracking shorter passwords, longer passwords, meta characters that don't necessarily belong in there. And what you would need in order to do that, you have a bit of Perl code here, which this doesn't actually work. There's a typo on it. But the concept is the same. You load in the form, you find all the form elements that you're after, and then you just print them out as a dynamic hash there. And then you put that in a file, and you just let John have a go at it. Yep. If you are using John with Jumbo, you can update the make file to enable MPI, so you can do distributed cracking across multiple hosts. MPI is pretty easy to set up. You create a host file, enable SSH authentication for your user, key-based authentication, so you can't rely on passwords, and then basically use MPI exec.john with whatever parameters you would normally do, and then MPI takes care of the rest. So it's really easy to do distributed stuff with MPI. However, you're better off using GPU. It greatly outperforms CPU for hash calculations, scales by the number of GPU cores or devices that you have in your box. You can use either CUDA or OpenCL depending on what devices you have. And like I said, some cloud providers have an Amazon Office in NVIDIA, so you can use either CUDA or OpenCL. As to why you would choose one or the other, it really comes down to personal preference. Most of the modern tools tend to use OpenCL simply because CUDA only works with NVIDIA, OpenCL works with a plethora of things. There are some technical differences in the sense that CUDA you have to manage your own threading more than OpenCL will sort of manage distribution of tasks across the number of cores you have available. However, since I find CUDA a lot easier to deal with, partly because I suck at C coding and partly because CUDA actually allows you to do some things that aren't necessarily great with like buffer offsets and pointer traversals. So I wrote mine in CUDA, but there's no reason why you couldn't use OpenCL. There's plenty of open source options that you can use to build on. You don't necessarily have to build a cracker from the start. John the Ripper, like I mentioned. Crypto has Multiforcer, is another very comprehensive GPU-based cracker. Uses OpenCL and supports distributed cracking, but it doesn't use MPI. It has its own server-slave model. Wisecracker, had to play with it. Uses OpenCL and does distributed cracking over MPI, but it's basically just a proof of concept. White Pixel, diffuse GPU cracker. It's an CUDA-based one that supports multiple salts, so I based mine on that. OCL crack. Basically, have a look at it, see what compiles, or see what sort of coding style you're happy with, and then just build on it from there. There are other alternatives, but those are the ones that I sort of went with. So, for the demo, we're going to demo a number of different things. And I think we'll start off with, let's see how we're going to do this. Where's the key? Duplicate. All right. How does that work? Okay. That's all right. So the first demo is going to be based around the fact that if you have a hidden return a validation page, you can just brute force it. So I've written a very basic brute force script that spits out a whole bunch of lines. So you do something like that, and it basically gives you like a big list of files. You can choose to load that into burp, or pipe it to wget. I've got this. Sorry, let's move that up to the top. I don't know if you can read that, but it basically runs it. For the sake of brevity, I only grep for the ones that are relevant, and then in a loop, I do a head request, and if that head request returns a 200 OK, I'll echo the URL. So if we run that against my web shop instance here, it should come back fairly quickly with the valid URL. Yeah, there you go. So if that was like a hidden URL, you can sort of still find it just because humans tend to name these things in a sensible manner. And then once you find it, you can proceed with the other attacks. Oh, sorry. All right. Let's look at this. So we go to our web shop, and we start off. We want to buy a MacBook Air. A good price, I think. Yeah, just go with that. We'll go to the checkout page. We'll just sort of register as a new user. Sorry. Maybe have something a bit more recognizable. Maybe December. Some based in Melbourne, go with that. Scroll down a bit. Oops, sorry, okay, it doesn't like first name. That, okay. The demo one. Really? Should have prayed to the demigods. Sorry? Yeah, right. There we go. Yeah. Yeah, okay. There we go. Thank you for that. I agreed to terms of services, and then instead of actually making the payment, we'll get the DOM source, select all that, save that page, and call it order. And then we'll go back into our demo, and we'll do heads up, which gives us this dynamic hash, which we can use in John the Ripper. So if I go to my box in the cloud, I can, I've ran this before. The sad thing about, as you can see, this thing's been running for over 2 hours. John the Ripper is not particularly fast when you're using CPU. So rather than doing John the Ripper, we'll crack this in CUDA. It's slightly different in this case, so just takes it as arguments, some lazy. So we'll say the first bit here is the hash that we're going to crack, and then we give it a salt in front of the password, and then a salt behind the password, and we know that this is 6 characters. Now, I've chosen 6 just because I want the demo to go a bit faster. But basically, you adjust this based on what payment gateway you would be targeting, because they're all slightly different. So in this case, something isn't working. Oh no, there it is. So in this case, that's the password there. Once I know the password, I can go back into my demo. and then I can sign the request from order with the password. I'll generate a payment message, spoof a transaction ID, sign this, and then basically they give me this URL to visit. While we do this, see no new orders in my web shop. We go back to this one. We'll visit a spoofed URL. Just let that work out for a little bit. Alright, so order confirmed, order number 6, and then if we go in to my shop here, I'll see here I have a new order. Show all orders. Payment accepted, as you can see there, even though we didn't pay. We can also take advantage of unprotected parameters in this case. So, sorry, close the dumb selection. We'll go back to this one. So what we'll do is we'll make another order for the same amount. And then this time we'll register it as a different user. Scroll down a bit. Address. Oops, sorry, no, we don't want that. Okay. Choose delivery method, agree to terms of service. This time I'm not going to bother getting the DOM out because the shopping cart IDs are sequential, and since no one else is using it, I would normally extract the shopping cart ID because in this case the shopping cart ID is being ran in a we'll go back to this one. Shopping cart ID is being included here as a custom variable, and it's not protected by the signature. So we'll just take the one that we used for shopping cart number 7, the order we just placed. We'll rerun it, but in this time we'll make it for shopping cart number 8. And then that will run for a little while there. Alright, confirmed. This time order ID is 07. We can go back in here, show all orders, and then 7 here, and you can see that it says demo 2, payment received, even though we didn't pay. So it's also vulnerable to replay attacks and unprotected parameter tampering. So now for my next trick. Well, we're going to be looking at a SQL injection. So if I go to this one. Let's see, no, that one. No. So I have this, not that one. Yeah, this one here. If I go and have a look at my VM here, see that it runs MySQL proxy, and I have, there's an SQL injection in this one here. Let's see, have we got it here? Yeah. there's a pre-auth SQL injection. Part of the problem with having SQL injections in this case is that the shared secret has to be stored in plain text in the database in order for the merchant to be able to validate the requests coming in and that they're signed. So in this case, we could we can go visit this URL. That's how you do it. Copy paste failure. So if we do typical example, you can A equals B. Sorry, A or B in, so that doesn't really help. So it's a subselect. Better example, I guess, is if we bracket like that, you can see it loads straight away. We can go here and see that MySQL proxy has picked up the SQL injection. And also the page load for this is very fast. So once we take it back and the SQL statement is working, the benchmark makes it sleep. And so typical blind SQL injection, do that, extract the password, a couple of characters, and it's not going to take you that long. Once you have that, you can straight up spoof or hijack the API access on behalf of the merchant. Now with this one, they also happen to be quite helpful. That they have a debug log of curl requests made by the module. And so what we can do with that is just extract the credentials straight from there. So if we go to this, oh nice. You can see that we get HTTP basic in there, and then you could basically pipe that into base64 decode, get username and password straight away. So just oops. Yeah, what do we got? Ugh. It should be. Yeah, of course. So you'll see there that's the username, so password is sub123, and then base64 complaints because it's got DOS line endings, but that's not a problem. So as you can see from sort of the last two bugs, let me just go back to this, have some proper resolution. Sorry. Yeah. So once you have access to the API and you can sign requests, some of the other things you can do is issue your own refunds. So rather than spoofing payments, you can actually make a genuine payment. The payment will appear in the merchant's account. You'll get your goods, and then you'll just refund your own transaction. If you're feeling particularly evil, you can just loop through every possible transaction and refund all of them, which is a good way to get rid of your competition, I suppose. So in conclusion, don't rely on the browser to drive traffic between the merchant website and the payment gateway. Crypto is pretty hard. you can either use more than one unknown variable in request validation or use a long secret, or even better, use token-based redirection so that the browser never touches any of the transactional details. It's also recommended that you protect all the parameters used in the request. Use a HMAC so that you can't be attacked with key length extension attacks. However, even if they have weak request validation, it doesn't necessarily mean that they have an exploitable vulnerability. There are some mitigating factors around. Luckily, there will always be implementation bugs, which makes me happy and keeps me in job. If you do want to look for bugs in payment gateway implementation, the following places are a few good places to look. Vulnerable vendor code, arbitrary fault deletion, it's always handy. Bad SSL practices, this one is absolutely everywhere. There was like a bug in PHP that it wouldn't work with certain versions or certain patch levels of Windows. So basically, every PHP developer ever, to avoid breakage, turns off SSL verification by default. And even if you do enable it, in all the versions of PHP, having it enabled, it didn't actually do correct validation, so you can still man in the middle of them. And if it's more recent but not the very latest, pretty much every language has had bugs. Sort of at the end, mid last year, there was a whole bunch of them. CV 2013, something for PHP, one for Ruby, one for Python, one for Java. Basically, if the certificate common name had a null byte in it, it would terminate and just validate half the certificate name, or common name. So you can always man in the middle of these things if you happen to have access on the data center side. Another one is PHP type juggling. It's always good when comparing hashes in PHP. If you don't use the triple comparison operator, PHP will quite happily convert one hash to a float and treat the other hash as a string, trunk it to null and go, well, null is kind of similar to this float, so we'll claim that they match because typecast. So again, this thing isn't like every PHP plugin I've ever seen for payment gateways. They use the double comparison. So lots of bugs to be had. Any questions? No questions? All good? All right. These slides are actually a bit more updated than the ones that were on the CD. I spotted a couple of mistakes. So slide and demo code can be found here. I will be pushing to the Git repo sometime after I get off stage, so go grab them while they're fresh. Yeah, and that's it.